Now we have the last presenter of today's workshop, Professor Harry Asada. And then he's going to talk about his work on the symbiosis between the human and SuperLimbs. Professor Asada, please take it away. I think you're muted, Professor Asada.
Okay, can you hear me and can you see it?
Oh, good.
Okay,
yes.
Sorry, rule number one, you should not change your laptop when you have important Zoom meeting. So that's the lesson I got. But anyway, so thank you for inviting me. No, I'm one of the organizers. I forgot. Yeah, as Wendon said, and I'm going to talk about the symbiosis between the human and SuperLimbs. And I've been working on this crazy robot, supernumerary robotic limb. So you have a third arm, a fourth arm in the last about 10 years. And there are many places that you can attach your robots to do something interesting. And then unlike exoskeletons, although the robot is attached to our body, but it doesn't go along the human limbs, human joints. So it is free from human motions. So you can do many interesting jobs. But the challenge would be really how you create the symbiosis, and then communications and the controls turns out to be major issues. So it is an interesting areas for your investigating the human-robot symbiosis. So let me start with this part. So during COVID, e-commerce grown up very well, but we see those people carrying a big bags, and then we need to assist them. So we built this SuperLimb. Yeah, it's a long day, so let me start with something relaxing in the video. So this robot attached to my student's waist area, and then he can open the door while holding a big bag. So the question is how he is communicating with the robot. So this is very crude, simple device. We're going to elevator hold. You can stop the elevator. This is not the thing we recommend, but human, it's a robot hands, and also COVID friendly. Yeah, you don't need to use your fingers. And yeah, when
it's been so long, man. Yeah. Thanks. How are you? Nice to see you. How's it been?
Maybe that is good enough. So both hands are busy in holding this back, or sometimes both hands are busy for holding a grinding tools. Yet, and we want to communicate with our SuperLimbs, supernumerary robotic limbs. So, you can't actually use a hand to push buttons that we think. However, interestingly, holding a bag and holding this tools, actually, you pressurize all the 10 fingers in some way, but still you can change the distributions of forces among 10 fingers. So if you measure the human movement and how the 10 fingers are used, you can create the kind of the data matrix, and then taking the covariance matrix and analyze the principal components, you find that the certain modes dominate. And then actually the last few modes are basically not used. So this is the technique that we call the null space communications, because you can create some code to send a command to the robot while you are holding this, but I know you can just push the certain points which are in this null space. You have no interference with your main job, that is holding this object. So that's actually a communications. Well, first we had to do some voluntary controls and controlling our robots. But if the number of degree freedom increases, you can't do all manual operations, and you have to introduce some kind of autonomy. The robot motion should be coordinated with the human motion, and the robot motion must be natural and symbiotic. And how we really achieve that. And in that, let me show you, this is the old video, but let me just review it.
Robotics researchers are developing ways to add an extra pair of arms to your body.
The robot will try to act according to what I'm doing.
Robotic arms come to life thanks to artificial intelligence. The AI system monitors the wearer's arm movements, and eye trackers detect where the person is looking. From this data, it predicts the next movement of the wearer and automatically moves the robotic arms to a supporting position. No explicit human input is needed. The more you use the device, the more accurate the movements become as the AI system learns the way the wearer moves. The next area of research, adding extra fingers. Wearable robotics are extending the physical capability of human beings.
It is difficult to achieve comprehensive.
Yeah. So yeah, one thing I like to introduce as a methodology is a bio-artificial synergy. So we like to do something that very cohesive with the human motions, and it should be natural, right? And the neuromotor control theory synergy that can be extended to human-robot symbiosis. And what we like to do is we know that the central nervous system does not actually control any many details about the individual muscles, but instead it's actually controlled as a group, and coordinated motion can be created. So that's symbiosis, synergies. Now, interestingly, we can extend this to the systems with half human, half robot. In this case, 5 natural fingers, plus 2 extra robotic fingers, treating a 7-fingered hand as one body. How can we actually create the synergy among these 7 fingers? So this is the famous Santero's analysis. 19 joints, 5 fingers are coordinated. And then the first mode is to open close 5 fingers in phase. And then the second principal component is to twist the 5 fingers, and these 2 explain the over 80% of the data. Now we can extend it to the ones with the 2 additional robotic fingers. So you now have the 7 fingers, and then do the same type of experiment and asking the human subject to grasp these odd-shaped objects, and then ask them manually control these 2 robotic fingers to get the best the postures. And then we analyze the data. We found that the synergies among the 7 fingers, and then based on that, we can control the system. So here's the 19 joint of the human hand, and then the 2 robotic fingers, the 6 DOF, creating this actually extended data matrix. And then we analyze the principal component analysis. Boom, you get the first, the second, the third mode can explain the third, over 95% of the motions. So this is the first mode. All 7 fingers open, close in phase. And this is the second mode. It is a little bit complicated, but 2 robotic fingers are moving in a unique way, which is basically orthogonal to the first one. And then the third one is kind of twisting emotions. That is third significant mode. So we can do this kind of stuff. Now, our objective is not just finding the synergies among 7 fingers, but we like to control the 2 robotic fingers. So in this case, it is actually important to divide the entire data matrix into 2 parts. One is the input, only 19 joints of the human fingers. And then output side is actually robot fingers to be controlled. That's actually 60-dimensional quantities. If you apply the partial least squares regression, you can find the most correlated directions, input space and output space, thereby you can actually represent the relationship with the lower dimensional system, which is basically 3 components that are good enough to do it. So that's actually a quick overview of the things in terms of the voluntary controls and how you express and communicate the intention to the robot. And then also reactive controls, or this is a part of a type of autonomy. So following the human motions and how the robot can do the things autonomously. But if all the actually, if everything is autonomous, that means human has no means to express his or her intentions, right? So the human-robot symbiosis, we had to leave some part to the humans. Humans still do things as he or she wants to do. So balance must be made between the manual control, voluntary, and the autonomous autonomy, must be established, and the voluntary controlled and then reactive autonomous control must be integrated. And then the question is that let's see one hand, which is actually controlled in part by autonomy and in part by the human intention directly. That said, that how you divide the 6-dimensional space between the two, how you integrated these two, and that's a really interesting, human SuperLimb symbiosis. And we look at the special case. This is a hemiplegic patient, so he can't move the right side, but that's affected. So we replace it by a SuperLimb. So SuperLimbs hold the knife, and then functional hand hold the fork. And this is actually a very challenging by manual operations, how the SuperLimb can actually do the job together with the healthy hand. Now we did some data-driven approach. We took a measurement of knife and fork movement in terms of the tool displacement and then postures. And we analyze the data and then try to find the, some useful information. Number one is that among the 6 DOF motion needed for this knife, which subspace is to be controlled by, it can be controlled by the robot based on some kind of autonomy, some reactive control, and which subspace should be controlled by the human voluntary controls, rather than leaving everything to autonomy or other way around. So first we look at again the principal component analysis of 6 DOF motion of the knife, which is to be held by the SuperLimb. And it turns out again the first 3 components explain the most of the cases. So the point is that we like to actually combine voluntary controls and autonomy, kind of a machine learning should be brought in. Now, another very interesting symbiosis is that actuator side too, we can combine the robot actuators and the human muscles. And actually, some particular degrees of freedom, some direction to some mode to be not only controlled by the human, but also actuated by the human muscles. And that actually reduces the number of actuators needed. So that's a good thing from the design viewpoint. Only the remaining degrees of freedom are to be controlled with and powered by the robot actuators. And then that's also controlled by the some kind of autonomous controller. And then this is the experimental setup we have built, and actually 2 actuators driving some axis of this. And then also here's the cable drive systems to control this, with the human muscle. So, most important, interesting part is how you divide the space into 2. Assignment of human-robot DOF based on some of the predictability. So what we like to do is to generate the control command to this robot actuators, and that action must be predictable. as described in the artificial bio synergies, we'd like to relate that motions to some other measurable motions, such as the functional hand motion, holding and moving fork, that can be measured, and then that it can be actually used for predicting the knife motion. So we picked the few degrees of freedom which are most predictable. Most predictable. That's actually natural. But more interesting things is that well, least predictable degrees of freedom. What to do with it? Well, least predictable because of that the human motions are nothing correlated with the other part of the body, but he or she decide the things and he wants to do. So this particular part of subspace should be left to human decisions, voluntary emotions. We should not step into that to automate it, because otherwise human will be very frustrated, right? So human must retain some control authority, and then that is actually indicated in this subspace, which is least predictable. And so the rest of part is we just executed. So we measured the knife motions, and then excuse me, fork motions, and the knife motion must be predicted. And here we started with the healthy person, the demonstration data used as a ground truth. And then we like to predict this compared with the predictor output, and then this error is to be used for that analysis. And I also have to say that the some degrees of freedom, even the knife part is controlled by the human. That motion, that degrees of freedom can be used as the regressor to construct this prediction. So it turns out that I said that three principal components are basically explaining the most of the human motions. So first we look at the all possible combinations of the three components. It turns out the first and the second component to this component combination is most predictable. So most predictable, that means that this can be done with the autonomous control. And actually this predictable is V3, this component. This should be done with the human voluntary control. Also should be controlled powered by the human. So basically the autonomy is locating this knife position basically relative to the fork position. So as you move the fork and then the knife follows. On the other hand, some cutting motion at the end, we want to cut it, right? That's very much the human's decision to when start cutting and when to stop. It's not correlated with not much in other things, but that should be done based on the human voluntary control. So this is a quick video. And overall system view is basically this is a symbiosis. This is the robotic arm, and then the human body is connected to that. And and one interesting point is that we exploited the human power, and this particular degrees of freedom and human muscular motion actually the leg motion is transmitted to from that feet human foot to this actually knife cutting motion like this, and the others are actually collocations of basically the autonomy. So the cutting, you place this and then actually start cutting it and stopping. That actually a human discretion. And on the other hand, relocating the knife, it should be coordinated with the fork, and as you move the fork, the knife follows in a certain pattern, which is actually derived from the data. So that's actually the quick summary of the job we've been doing. A new data-driven method has been presented for integrating the voluntary control and the reactive control. For particular case study of by manual manipulations. And using a measure of predictability, we have found that the most predictable motions of the SuperLimb can be assigned to the reactive control and robot DOF powered by robotic actuators. And the least predictable part is to be left to human, and then that's also powered by the human motion. This is my group, and this is my sponsors.